Hello everyone. In this video, I'll discuss a very commonly asked interview question. What is the difference between ASIC design and FPGA design? To clearly list the differences, it is important to first know what ASICs and FPGA are and to understand their respective design flows. First, let's understand what an ASIC is. The acronym or the short form ASIC stands for Application Specific Integrated Circuit. As the name suggests, an ASIC is an integrated circuit designed for a specific application or function. In the case of an ASIC, the chip is designed and fabricated from scratch to meet the exact requirements of a given application. Once manufactured, the functionality of the chip is fixed. It cannot be changed. Examples of application-specific ICs include consumer electronics used in smartphones, smart TV, and game consoles for tasks such as graphics rendering and audio processing, etc. Or another common example from daily life is telecommunication and networking ICs used in routers, switches, modems, which are optimized for high-speed data processing. Because an ASIC is tailored for a specific use case, it can be highly optimized for performance, power consumption, and silicon area. However, it has high cost and long design cycle. Now let's discuss the ASIC design flow step by step. The ASIC design process begins with ideation and specification, where the system requirements such as functionality, performance, and power constraints are defined for a specific application. These specifications are translated into a high-level architecture, which is then implemented as RTL using hardware description languages such as Verilog or VHDL. The RTL is then synthesized into a gate-level netlist and optimized for area, power, and performance. Next, physical design is performed to create the silicon layout from the gate-level netlist. Throughout the flow, the design is continuously verified for functionality, timing, and power, and updated if issues are found. After final sign-off, the design is sent to a semiconductor foundry such as TSMC or Intel for fabrication and packaging. The manufactured chip is then tested in the lab to ensure it meets all specifications. Once verified, the functional IC is shipped into the market. Now let's talk about FPGAs. FPGA stands for Field Programmable Gate Array. An FPGA is a reconfigurable integrated circuit that contains programmable logic blocks and programmable interconnect. FPGAs with varying specifications such as logic capacity, on-chip memory, and specialized features are commercially available from companies like Intel and AMD. Designers can program FPGA chips to implement custom digital hardware for an application. From architecture perspective, a generic FPGA consists of configurable logic blocks, CLBs, connected by programmable interconnects. CLBs are the fundamental building blocks of an FPGA. Each CLB typically contains lookup table, flip-flops, and multiplexers, which can be combined to implement complex digital circuits. A lookup table is a small memory that stores predefined output values for all possible combination of its inputs. Instead of computing logic functions using gate, the FPGA retrieves the output directly from the lookup table, making it a fast and flexible way to implement logic. Programmable interconnects form a network of wires and switches that connect the CLBs together, allowing designers to define how data flows through the circuit. One of the key advantages of FPGAs is their reconfigurability. The internal logic blocks and the interconnects can be reprogrammed to perform different functions, even after the device has been deployed in the field. Now let's look at the FPGA design flow, which is much simpler and shorter compared to the ASIC design flow. In FPGA flow, the intended chip specifications are implemented using hardware description languages such as Verilog and VHDL. Then the design is synthesized into a netlist, verified, and finally programmed onto a pre-built FPGA to achieve the desired function. Unlike ASIC design, this process does not involve creating custom ICs. Instead, it configures existing hardware resources on the FPGA to meet the specific application requirements. Now that we understood what ASICs and FPGA are, along with their respective design flows, let's compare their unique advantages and disadvantages. This comparison is important for selecting the appropriate technology for a given application and for justifying that choice. From a performance perspective, ASICs significantly outperform FPGAs. Since ASICs are custom designed for a specific application, they can be highly optimized for maximum efficiency and speed. ASICs also have an advantage in power consumption. By optimizing the design for a specific function, designers can minimize the number of active components and significantly reduce power usage compared to FPGA. On the initial development cost front, FPGAs are clear winner. Unlike ASICs, which require substantial upfront investment in design and fabrication, FPGAs have much lower initial costs. This makes them a cost-effective option for early prototyping or low-volume production. Although the initial investment for ASIC design and fabrication is high, the per unit cost decreases significantly as the production volume increases, making ASICs more economical for high volume manufacturing. From the development cycle time perspective, ASIC design process is time consuming and can take several months or even years to complete. This long development cycle can be a disadvantage in fast-paced industries where rapid product development and the time to market are critical. In contrast, FPGAs provide a much quicker path for early prototyping and hardware validation. Another aspect where FPGAs win over ASICs is their flexibility. For ASICs, once an ASIC is designed and fabricated, its functionality is fixed and it cannot be changed without redesigning and manufacturing a new chip. In contrast, FPGA-based designs are highly flexible. Designers can use hardware description languages such as Verilog and VHDL along with FPGA design tools to reconfigure the device and map new functionality on the available programmable logic and interconnects without starting from the scratch for each new application. These were some of the important differences between ASICs and FPGAs. That's all for this video. I hope you find it helpful.